Alright guys, how's it going? I'm back a bit faster than some of you perhaps expected, with a little bonus video, which should hopefully set the record straight on at least one of Nvidia's Ampere talking points. Every graphics card or CPU release always brings the most rabid fanboys and idiots out of the woodwork, and my YouTube comment section has been a right old chuckle this past week. Some real gems in there, I assure you. But perhaps most surprising to me was the constant barrage of comments telling me that no, Ampere does not have 10,000 plus CUDA cores. That's just Nvidia marketing, and it's only 5,000 CUDA cores and a bunch more in a similar mold. I have had so many comments on YouTube and on Twitter suggesting the same thing. And so today I will analyse this single point. How many CUDA cores does Ampere really have? And who knows, I might even unearth something unexpected. Back in 2010, Nvidia launched Fermi, and the tech meme scene was never the same again. I've covered that plenty in the past. This video will be somewhat more serious though, so that means taking a look at the Nvidia Fermi Compute Architecture white paper. The good thing about white papers is they are generally safe or safer from marketing crap, and they contain details at high and low enough levels that anyone with a reasonable interest in the subject can at least figure out what's going on. So we will start at page 7 and an overview of the Fermi architecture. As I mentioned in the previous video, the flagship Fermi chip GF100 had 512 CUDA cores. And honestly, I love these block diagrams as they make the numbers clear to see. It's quite a lot of green boxes there, right? Guess how many? 512. So we can assume correctly that each green box here is what Nvidia calls a CUDA core. And these 512 cores are organised into 16 SMs, streaming multiprocessors, of 32 cores each. You can count them 1, 2, 3, 4, 5, 6, 7, 8, double that for 16. And all this other stuff around the edges like the memory controllers, they're not really important for this video. Right, so we've got 512 cores organised into 16 streaming multiprocessors. On the next page, we get a close-up of one streaming multiprocessor. At the top, we can see stuff like the instruction cache, warp schedulers, dispatch units, and the register file. Think of all of this as the front end, where the threads are prepared for work by the CUDA cores, the green boxes. Each of these individual CUDA cores within the SM executes a floating point or integer instruction for one of these threads. And we can see that zooming into one CUDA core, that each of them contain an FP unit and an int unit. That's floating point and integer. And these FP and int units are literally one-trick ponies. They perform work on either floating point or on integer numbers. This operand thing here. And then they kick out the result. You've probably heard terms like FP16, FP32, FP64, int8, int16, int32, etc. The number after FP or int is how precise the number that enters the unit can be worked on. Faster a GPU can do these calculations, the higher the frame rate. And the two most obvious methods of increasing the speed of these calculations is by either increasing the clock speed of the graphics card or by increasing the number of these CUDA cores. But to finish on Fermi and going back to the streaming multiprocessor again, we can see other stuff like load store and caches. And that's really all about keeping the most frequently and recently used data nearby. And these SFUs here are special function units, which do the crazy stuff like square roots, sine and cosine. The kind of thing that would completely jam up a bunch of these CUDA cores due to the complexity of the operation. And that's about as simple as I can explain it. So moving on to Kepler 2 years later. Kepler, as I said in the last video, is what I consider to be the first of the new age of Nvidia GPUs. CUDA core count was tripled from 512 in Fermi to 1536 in Kepler. And as I also noted in the previous video, this wasn't even the flagship chip. Just look at all those green boxes though. How did Nvidia manage such a feat? There were a couple of reasons for it. First of all, Fermi was built on TSMC's 40nm node, and Kepler was on the new 28nm node. And so with the shrinking chip sizes, more of these CUDA cores could be crammed into the same die space, and Nvidia took advantage of that. Fermi CUDA cores were also very capable of performing stuff like FP64 operations. That's what's known as double precision. And those kind of numbers are used in high performance computing, quantum chemistry, simulations, that kind of thing. Nvidia cut a lot of that capability out of their GK104, the early Kepler die. And so therefore that had very weak FP64 performance compared to Fermi. But what it did do was it saved an awful lot of die space, essentially a lot more but much weaker cores when it came to crunching certain numbers. The real Kepler flagship, GK110, that actually had another large improvement in FP64, and it also came with a very large die size, similar to Fermi. And with Kepler, we first heard about the GPC, or the Graphics Processing Cluster. And this is like the dominant high-level block in Nvidia GPUs, until this day in fact. And we can see that the GTX 680 has 4 of these GPCs, each of them containing 2 SMXs, which is just what Nvidia called them instead of SMs, with each of the SMXs housing 192 CUDA cores. But basically speaking, you can count all these green boxes and you'll get to a total of 1,536 CUDA cores for the GTX 680, and that is how it was advertised by Nvidia back in 2012. Nvidia's next architecture was Maxwell in 2014. Looking at the block diagram of GM204, which was in the GTX 980 graphics card, we can quickly see how the architecture changed again. There are still 4 GPCs, or graphics processing clusters, but now each GPC hosts 4 SMMs, as Nvidia was now calling them. If we zoom in, we can see the layout has changed quite a lot. Even though there are 4 SMMs compared to only 2 in Kepler, the number of CUDA cores per SMM is lower, down from 128 from Kepler's 192. And these kind of architectural changes are mostly about balancing the GPU and lessening bottlenecks that they had discovered in the previous generation. While everybody loves Maxwell because it was an amazing performance per watt increase over Kepler on that same old 28nm node, it's important to note that a lot of the extra gains came from larger chips. GM204 here was 35% larger than GK104. That's why it had more CUDA cores overall. Maxwell also trimmed down the integer unit inside of the CUDA core. And if we look at the CUDA toolkit documentation, Kepler here is number 3 and Maxwell number 5. We can see that Kepler's integer unit was capable of dedicated multiplication instructions. However, this capability was removed in Maxwell. It required multiple instructions to do the same thing. And the point I'm making here is, these are still CUDA cores, but instructions are being added and removed generation to generation. There's not a huge amount more to talk about with that. Maxwell was just better at gaming than Kepler due to a combination of fixes and optimizations. With 128 CUDA cores per SMM and 512 per GPC, GM204 had 2,048 CUDA cores in total, and they can all be counted if you like. Next up for Nvidia in 2016 was Maxwell on Speed, better known as Pascal. Feel free to be as upset as you like with me over that description, but looking at the block diagram for GP104, the successor to GM204, shows the same 4 GPC and the same 128 CUDA cores per SM, which is what Nvidia was now calling the SMM in Maxwell, previously known as the SMX in Kepler. The only difference is that each of these GPCs had one more SM for an extra 128 CUDA cores per GPC, or another 512 in the total GP104 chip. That's why when Maxwell GM204 had 2048 CUDA cores, the Pascal GP104 had 2560. There were a few more minor changes in the Pascal architecture, but this series, while blazing fast and very efficient, was just a little bit too boring to truly grab me from an architectural standpoint. And so moving on then to something completely different. Nobody loves Turing, except for me it seems. Sure, it wasn't impressive from a performance standpoint. It's not really easy to impress versus the speed demon like Pascal was, when you're basically stuck in the same node. Then you just shove a bunch of extra ray tracing and tensor hardware onto the die. But Turing went further than just slapping on some bells and whistles. It was yet another major architectural change to the SM, While Maxwell and Pascal had 128 CUDA cores per SM, Pascal had dropped down to 64, 16 FP32 in each of these 4 slices. But this is all just one SM. And to make up for that reduction in the number of CUDA cores, there were of course more SMs crammed into each chip. As you can see, there are very many more in fact, as this is TU102, which was actually the flagship Turing. So direct comparisons with the previous 2 white papers covering the mid-range GM204 and GP104 aren't apples to apples. But in the table below, we can see how Turing's layout had changed by quite a bit. The GPC count stayed the same versus Maxwell and Pascal flagships at 6 each. But Turing's SM count was up to 72 on the full chip versus 30 on the full Pascal GP102. So even with the halving of CUDA cores per SM, having more than double the number of SMs meant that Turing had 20% more CUDA cores in total. And we can see that there, 4608 is 20% more than 3840. And this 4608 number will be important. Now, one reason why that is that Turing brought another major architectural change. At the start of this video, we saw that with Fermi, each individual CUDA core had both a floating point and an integer unit, each 32-bit precision capable. And this same layout, as far as I'm aware at least, remained through Kepler, Maxwell and Pascal. There would have been small changes to either FP64 capability, or as I mentioned, Maxwell for sure had a trimmed integer unit, less capable of multiplication. And that would of course have carried over to Pascal too. But basically speaking, from Maxwell to Pascal at least, each CUDA core was capable of doing either floating point or integer operations, but not both at the same time. The major change in Turing was that the SM now split the FP32 and int32 data paths. Previously, each CUDA core did one or the other. Now Turing could run both floating point and integer maths concurrently. And the reason behind this change was that Nvidia realised that for every 100 floating point instructions, there was an average of 36 integer pipe instructions, which works out at around about 26% of all instructions. Turing implements a major revamping of the core execution data paths. Modern shader workloads typically have a mix of FP arithmetic instructions, such as floating point add or multiply add, with simpler instructions such as integer adds for addressing and fetching data, floating point compare or min-max for processing results, etc. In previous shader architectures, the floating point math data path sits idle whenever one of these non-FP math instructions runs, as you just heard, either FP or int, but not both the same time. However, Turing adds a second parallel execution unit next to every CUDA core that executes these instructions in parallel with floating point math. So what seems to have happened is that the CUDA core as we knew it before was split in two, creating 2 independent int and floating point data paths. So with Turing came these new integer cores, as they were called. And it's important also to note that the Kepler stuff like dedicated multiply, the one that we saw in Kepler and the one that was missing in both Maxwell and Pascal, this also came back with Turing. So Turing's integer unit was also more fully featured than Maxwell's and Pascal's. But now that int and FP could be executed concurrently, floating point, the majority of graphics workloads, would no longer be halted by much simpler integer math. And this is one of the reasons why Turing had higher IPC than Pascal. Because yes, it could actually execute more instructions per clock, so long as they were integer operations running concurrently with floating point. The interesting thing about this is that even with the addition of all of those integer cores, Turing was still only marketed as having 4,608 CUDA cores maximum, not 9,216. Nvidia didn't claim double the number of CUDA cores, because these integer cores were not capable of FP32, which remains the major workload in computer graphics. And so finally, that brings us to Ampere, and the talking point of just how many CUDA cores does Ampere really have? The answer to that being, Ampere has 10,752 CUDA cores. And yes, a lot here is going to depend on your definition of exactly what a core is. But hopefully this video has shown you that the cores are changing all the time, from series to series. But reading through the GA102 white paper, which I borrowed, we see what Nvidia believes CUDA core is. 2x FP32 processing. As you're well aware by now, most graphics workloads are composed of 32-bit floating point FP32 operations. Continuing with, the streaming multiprocessor SM in the Ampere GA10 GPU architecture has been designed to support double-speed processing for FP32 operations. That part was interesting, very similar to what Jensen said in his presentation about twice the number of shader operations per clock. And next, as we just heard, in the Turing generation, each of the 4 SM processing blocks, also called partitions, and I called them slices, they each had 2 primary data paths, int and fp, but only one could process FP32 operations. The other data path was limited to integer operations, one FP32 and one integer 32 path in Turing. But now, GA10X Ampere includes FP32 processing on both data paths, doubling the peak processing rate for FP32 operations. The result of which, the GeForce RTX 3090 delivers over 35 FP32 teraflops, an improvement of over 2x compared to Turing GPUs. And finally, to get the whole picture, one data path in each partition consists of 16 FP32 CUDA cores capable of executing 16 FP32 operations per clock. So that'll be this one. Another data path consists of both 16 FP32 CUDA cores and 16 int32 cores, and is capable of executing either 16 FP32 operations or 16 int32 operations per clock. And so, with that we can imagine what has happened to the CUDA cores over the years. Again, there's no way for me to know if this is exactly true or not, at least not without a whole lot more research than anyone can be expected to do in one day. But anyway, Fermi, 512 CUDA cores, which according to Nvidia back then, each processor had a fully pipelined integer arithmetic logic unit, ALU, and floating point unit, FPU. Reading into that, it would seem that FP and int could be run concurrently on Fermi, but don't quote me on that. But clearly we can see the individual units inside each CUDA core. With Kepler, this FP and int setup remained, although doubtless there were some slight changes to the exact capability, and it was almost certainly trimmed down in some fashion to accommodate the huge increase in CUDA cores overall. Maxwell definitely trimmed the integer unit further, removing dedicated multiplication, and for sure by this point, concurrent execution of int and floating point was definitely no longer possible. It could have been possible during Kepler, I'm not sure, but by Maxwell, concurrent execution was definitely not happening. Pascal was no different. In fact, I showed you the same SM. It is almost identical to the Maxwell SMM. And looking at the CUDA toolkit documentation shows that numbers 5 and 6, or 6.1 at least, are identical in every way. Turing brought the biggest change, splitting the CUDA cores int and FP data paths, while also beefing up the integer unit again to Kepler levels and beyond. And now we can pretty much figure that Ampere has added FP32 cores to the integer data path that was split in Turing. All these ones here have gained an FP32 unit in Ampere. However, unlike Turing, there is no separation of path between FP32 and integer 32, which kind of means that this data path here is very similar to the Maxwell and Pascal generation, which is to say that either floating point or integer can be executed on this data path. And the end result of that is Ampere can run either 2 FP32 operations per clock cycle. That's 10,752 CUDA cores worth of FP32, or 1 FP32 and 1 int32 operation per clock. And it goes a long way to explaining why the RTX 30 series gets nowhere near its theoretical FP32 teraflops value while gaming. The RTX 3080 has 3 times the number of FP32 cores of the 2080, yet it only performs on average 60 to 70% faster at 4K and just under 50% faster than the 2080 at 1440p. But right, a quick summary. Ampere GA1002 has 10,752 CUDA cores. Nvidia is correct to consider FP32 as the real graphics core, as that has always been the major workload for graphics. In the majority of cases, Ampere's architecture will work as Nvidia intended it to. What's noteworthy here is that performance, and I mean overall performance. Forget all about the number of CUDA cores or teraflops for a minute. Overall performance is pretty good. The cards are just hot because of the older 8nm node. On paper, it looks bad because each individual SM could theoretically be bottlenecked by integer to the tune of 50%, which means that in some corner cases, performance could be barely ahead of Turing. However, that should only happen in very badly optimized titles. It's very likely that optimizations will increase performance by a decent margin, possibly even more than usual as developers begin to understand the architecture that bit better. Integers can be optimized at the SM level, leaving floating point to stretch its legs where it matters. Ampere is yet another major architectural advance for Nvidia, and I can already see what they have planned next. This FP32-inch sharing problem, that will go away. I will guarantee you that will go away as they split this new data path, just like they did with Turing before. And TSMC 5nm, if that is the next node, that will shrink this large 628mm die by more than double. Clock speeds seem sure to hit 2 GHz plus. And even if AMD can somehow take advantage of Ampere's weak node this time around, what comes next from Nvidia should have them very, very afraid. I'll catch you later, guys.